Hello everyone, myself Dr. Tarkeshwari Verma from CSVTU. In the last lecture, we discussed about the definition of the Fermi level and Fermi level energy, Fermi level in a p-type semiconductor and n-type of semiconductor and their work process and effect of the temperature on it, how its position vary according to varying the temperature, and learn about the Fermi-Dirac distribution and concept of Fermi level energy and Fermi-Dirac distribution are the fundamental understanding and behavior of electron in solid state context, particularly in the material science and condensed matter physics. Here are some important applications of Fermi energy and Fermi-Dirac distribution are presented. First is electrical conductivity. In a solid material, the Fermi energy determines the highest energy level occupied the electron at 0 temperature. The electrical conductivity of material is strongly influenced by availability of empty energy state above the Fermi energy. Material with a higher density of state above the Fermi energy are generally more conductive. Second one is the application in a field of semiconductors and band theory. The Fermi energy plays crucial role in determining whether a material behave as a insulator, semiconductor or conductor. In a band theory, the energy band like valence band and conduction band in a solid are separated by band gap. The position of Fermi energy is with respect to this band gap influenced by electric properties of the material. Third application in the field of doping and carrier concentration. Doping is the international introduction of the impurity into the semiconductor material to modify its electrical properties. The Fermi-Dirac distribution helps to understanding how the concentration of charge carriers in a material changes with the temperature or doping concentration. Fourth is thermoelectrical materials. The efficiency of the thermoelectric material with convert heat into electricity and vice versa depends on the electric conductivity and the Seebeck conflict. The Fermi-Dirac distribution is used to model the distribution of charge carriers energy which affect the transport properties and thus the efficiency of thermoelectric material. Fifth, optoelectronic devices. Devices like light emitting diodes and solar cell rely on the interaction of electrons and holes. The Fermi energy and Fermi-Dirac distribution are crucial for the understanding the behavior of these charge carriers and their recombination process, which are essential for the operation of optoelectronic devices. Sixth one, thermal properties. The Fermi-Dirac distribution is also used to calculate the heat capacity and other thermal properties of the material. As the describe the distribution of energy level occupied by electrons at different temperature. And next application in the field of quantum mechanics and quantum statistics. The Fermi-Dirac distribution is the one of the most fundamental statistical distribution used to describe the distribution of the particle in a quantum mechanical system. It is the important for the understanding the behavior of particles obey the Pauli exclusive principle such as the electron in a solid. Next one is the superconductivity. The context of superconductors, the Fermi energy and the Fermi-Dirac distribution are crucial for describing the formation of copper pairs which are responsible for the phenomena of the zero electric resistance and the perfect dimagnetism exhibited by superconducting materials. These are the just few examples of the numerous application of Fermi energy and Fermi-Dirac distribution in the field of material science, condensed matter, physics, and these are the just a few examples of the numerous application of the Fermi energy and Fermi-Dirac distribution in the field of material science, condensed matter physics, and electronic devices. These concepts provide the foundation for the understanding the electronic and thermal properties of the material in the quantum level. Now, today's we are discussing about the topic. The content of the today's lecture is, first one is the properties of carriers in a semiconductor materials, second one is the carrier drift, third drift current, fourth drift velocity, next one is the electron mobility. First topic is the drift. We should know what is the meaning of the drift. Drift refers to the slow movement toward the thing or object. The average velocity of charged particle in a material due to an electric field is known as the drift velocity. In this session, let me learn about detail about the drift velocity. Subatomic particle like electron move the random direction all the time. When electrons are subjected to the electric field, they move randomly but they slowly drift in a one direction, in the direction of the electric field applied. The net velocity which this electron drift is known as the drift velocity. We also describe the drift velocity in a term of the average velocity attained by charged particle in a material due to an electric field. That have, in a case of SI unit, the drift velocity is the meter per second. The net velocity of the electrons is every material above the zero temperature which can conduct light like metal. We have some free electrons moving at random velocity. When a potential is applied around conductor, the electron will tend to move toward the positive potential, but they will collide with atom and will become back to lose some their kinetic energy. However, due to electric field, the electrons will accelerate back again, and these random collision will keep helping, but the acceleration is always in a same direction. Due to electric field, the net velocity of the electron will also be the same in a direction. Drift motion of electrons refer to the slow and steady movement of electron in response to an electric field. This motion is distinct from the random thermal motion of electrons, which occurs due to their kinetic energy. Drift motion is characterized by a net directional movement of electron under the influence of an applied electric field, typically in a conductive medium like wire or a semiconductor. There are the two main types of the motion of electron. First is the electron mobility, second is the drift. Electron mobility refers to the average drift velocity of the electron per unit electric field. It is the measure of how easily electron can be moved through the material in a response to an applied electric field. Material with high electron mobility allow electrons to move more easily and quickly, while material with low electron mobility impede their motion. The concept of the electron's mobility is particularly important in semiconductors and other material used in electronic devices. There are the two primary types of the electron mobility. One is the electron drift mobility and second one is the Hall mobility. First, now we understand what mean by electron drift mobility. This refers to the mobility of electron is response to an electric field. It is commonly used to describe the movement of the charge carriers in a semiconductor. Second one is the Hall mobility. Hall mobility involves the motion of the electrons in a presence of both an electric field and a particular magnetic field. It is the often used to characterize the behavior of charge carriers in a material like conductive metals. Drift velocity. The drift velocity of the electron can be affected by factors like strength of the electric field, density of the electrons, and material conductivity and presence of the impurities or defects. Drift motion of the electron is the fundamental to functioning of many electronic devices, including transistor, diode, integrated circuit. The control movement of the electrons through the conductive path is the essential for the carrying out various electronic operation and information processing. In summary, the drift motion of the electrons involve their steady movement is the response to the electric field, with electron mobility and drift velocity being a key concept to use and describe the quality of this motion. Next topic is relation between drift velocity and electric current. We know mobility is always positive quantity and depend on the nature of the charge carriers. The drift velocity of the electron is very small, usually in a term of 10 raised to the power minus 3 meter per second. Hence, This velocity will be take approx 17 minutes for electron pass through the conductor of 1 meter. But surprisingly, we can turn on the electronic application is our home at lighting speed, which is the flick of the switch. This because of the electric current is not established with the drift velocity, but the speed of light. As soon as electric field is established, the current starts flowing inside the conductor and the speed of the light and not at the speed at which the electrons are drifting. Hence, there is the negligible small delay between the input and output is turning on the electric bulb. Relation between the drift velocity and current density. We can define current density as a total amount of current passing through the unit in a cross section is the conductor in a per unit. Another is the equation state that J is equal to 1 by A is equal to NVQ, where J is the current density measured in the ampere per square meter. V is the drift velocity of the electron. We can say that drift velocity is the electrons and their current density are the directly proportional to the each other. Always when the electric field intensity increases, the drift velocity increases and the current flowing through the conductor also increases. Electron mobility is the crucial concept in a field of electronics and semiconductor physics. It plays a significant role in determining the how quickly and efficiently electron can be moved through the material in response to an electric field. Here are some properties and advantages of electrons mobilities. First is conduction efficiency. Material with the high electron mobility allow for the efficient conduction of electrical current. In electronic devices like transistor and a integrated circuit, rapid and efficient movement of electrons is essential for the achieving high speed and reliable operation. Second, device performance. Electron mobility directly affect the performance of the electronic devices. Material with higher electron mobility can support faster switching speed, lower power consumption and improved overall device performance. Semiconductor devices. Electron mobility is a critical parameter in a semiconductor devices like transistor, amplifier or a switch electrical signal by controlling a flow of electron. Higher electron mobility enable transistor to operate more efficiency and at higher frequencies. 4 is the signal propagation. In communication system, electron mobility affect the speed at which electronic signal travel through conductive pathway. Higher electron mobility lead to reduced signal delay and better signal integrity. 5 is the reduced heating. Efficient electron mobility means that electron can move through the material with less resistance. Lower resistance result in a less energy loss as a heat, which is the important for maintaining the efficiency and longevity of electron components. 6 is the low power consumption. Electron mobility is linked to the power consumption of electronic devices. When electrons move more easily, it required less energy to drive them through the material. This is especially important in a battery powered device where power efficiency is critical. 7 is the semiconductors design. Semiconductor material with a higher electron mobility R is the favored in a design of electric components and circuit. Engineers and designers choose material that optimize electron mobility to achieve desired performance characteristics. 8 is the high frequency application. In an application involving high frequency signal such as a radio frequency communication and microwave technology, high electron mobility enable better signal handling and faster response time. Material selection. Electron mobility is a key consideration when selecting materials for specific application. For example, in designing semiconductor or a different function from the microprocessor to sensor, the choice of the material with suitable electron mobility can significantly impact device performance. Then research and development. Understanding the improving electron mobility in various material in an outgoing area of research. Researchers strive the enhanced material with high electron mobility to push the boundaries of electronic device performance. In summary, electron mobility is the fundamental property that outdisputes the efficiency, speed and overall functionality of electronic devices and circuits. It is the critical factor in advancing technology and enable the development of faster, more efficient and more capable electronic system. Now, we have some properties and advantage of drift velocity. Like drift velocity is the concept to use to describe the average velocity which charged particle such electron move in a response in an electric field in a conductive material. This concept is the particularly important in the field of the electronics, semiconductor physics. Here some properties and advantage are describing. First is the current flow. Drift velocity is directly linked to the flow of electric current in a material. When an electric field is applied, charged particle experience a net drift motion is the particular direction contributing to movement of electrical charge through the material. Second one, Ohm's law. Drift velocity is a fundamental component of Ohm's law, which states that current flowing through the conductor is directly proportional to the voltage across it and inversely proportional to its resistance. The drift velocity plays a role in determining the based on the applied voltage and the material properties. Conduction in conductors. In a conductive material like metal, where electrons are primary charge carriers, drift velocity is the responsible for the movement of electrons that constitute electric current. Fourth is the semiconductor operation. In a semiconductors, the controlled manipulation of drift velocity is essential for the various device functions. Devices like transistor and diode rely on the control movement of the charge carriers to achieve specific operation like amplification and switching. velocity also used in a signal propagation. Drift velocity determines the speed at which charge carriers move through the material in a response to an electric field. In a communication system such as the wired network and transmission lines, higher drift velocities leads to the faster signal proportional and reduced signal delays. Sixth one is the heat dissipation. Efficient drift motion can be contributed to reduce energy loss from the heat during the current flow. This is the especially important in an application where power efficiency and heat management are critical concern. 7 is the device performance. The behavior of the electronic device is often influenced by the drift velocity and charge carriers. Higher drift velocities can result in a faster device response time, improved switching speed and better overall device performance. Next one is our application is power electronics. In a power electronics applications such as the power converters and motor drive the movement of the charged particles determine how efficiently energy is covered and delivered. Optimizing drift velocity can lead to more efficient power conversion. 9 is the material selection. Drift velocity is the consideration when selecting material for the specific application. For example, certain semiconductor with a higher mobility may be chosen to achieve faster drift velocities, enhancing the performance of the electronic devices. Research and design. Understanding the controlling drift velocity is essential for the advancing semiconductor technology. Researchers and engineers work to design material, structure and device that optimize drift velocity for desired function. So, drift velocity is the fundamental properties that influence the current flow, device performance, signal propagation and power efficiency in an electronic system. It underpins the operation of various electronics components and plays a significant role in advancing technology for wide range application. In the next lecture, we will discuss about the current density, conductivity and electric field, relation between the conductivity and mobility in a semiconductors. Thank you.